Hello and welcome to our next product demonstration with Fair-Rite Products. I'm Jennifer Arroyo, Editorial Director for Interference Technology. Thank you for tuning into the program today. This demonstration will be presented by Bruce Sparrow, the Product Manager of Suppression Applications, and Michael Arison, Power and Inductive Products Manager. Bruce and Michael will explain how different beads work to suppress EMI noise and review an assortment of materials to suppress frequencies from 100 kilohertz into the gigahertz range. We'll have a Q&A with them at the end of the session, so enter any questions you have while you listen into the Q&A panel. Ready when you are, gentlemen.
Hello, and thank you for attending our webinar on how to choose the right Ferrite Snap-it core for EMI mitigation. Fair-Rite Products manufactures a wide variety of Ferrite components for EMC compliance, power, and inductive applications. We will give you a brief overview of how Ferrite is made, how it works to reduce EMI, which Ferrite to choose for a given frequency range, and finally we will have a practical demonstration of Ferrite EMI attenuation in the electrical lab. Ferrite is a soft magnetic material formed by pressing metal oxides and firing in a high-temperature kiln. Once fired, the ferrite powder takes on a hard crystalline ceramic structure. If a magnetizing force is applied to the ferrite, a flux field will be created. If we remove the magnetizing force, the flux field will disappear. The permeability of a ferrite core is a measure of the ferrite's ability to create a magnetic field. There are two basic types of ferrite, manganese zinc and nickel zinc. Manganese zinc will typically have higher initial permeability than the nickel zinc types. Ferrites used to reduce EMI become highly resistive at high frequencies and will act to absorb the electromagnetic interference. And although today our discussion focuses on EMI suppression, ferrites can also be used in inductive, power, and shielding applications. The impedance of a ferrite core is a combination of the inductive reactance at low frequencies and the ferrite's resistance at higher frequencies. Ferrite can be thought of as a variable resistor that is frequency dependent. Different blends of ferrite combined with different processing parameters gives us the ability to offer ferrite products that target different frequency ranges of unwanted EMI. By varying the constituents of the oxide powder mix prior to firing, we can attain different electrical parameters in the finished ferrite. These constituents are primarily iron oxide, manganese oxide, zinc oxide, nickel oxide, and binding agents. Powder preparation is a complex process involving batching and mixing, a calcine pre-fire, milling, and the addition of binders and lubricants. Quality control of the powder mix is monitored using X-ray fluorescence. The nickel-zinc ferrites have lower permeabilities and are useful for EMI attenuation at higher frequencies. The higher permeability manganese-zinc ferrites are useful for EMI attenuation at lower frequencies. Knowing which frequencies you want to attenuate is important to the proper selection of the ferrite core. Most ferrites are formed by compaction pressing. The typical setup consists of an upper and lower punch held within a die. It is critical that the density of the press part be consistent to maintain predictable electrical performance. Different sized parts require different press tonnages to achieve this uniformity. Press tools are designed in-house and press parts are pressed 5 to 20% oversized to account for shrinkage during the firing process. Some parts have intricate detail or are too large for compaction pressing. For these parts, Fair-Rite Products utilizes CNC machining as well as injection molding. After compaction pressing, the parts are in what is known as the green state and are ready for kiln firing. Fair-Rite Products utilizes both tunnel kilns and batch kilns for this process. Different temperature profiles are used during firing to obtain different electrical results. Temperatures as high as 2600 degrees Fahrenheit are reached in the kiln and burn off the binding agents and finally crystallize the ferrite and shrinking it to its final dimensions. Nickel-zinc ferrites fire in oxygen-nitrogen-air atmosphere, whereas manganese-zinc ferrites require a nitrogen-reducing atmosphere during firing. Ferrites are finished to their final dimensions and surface quality by burnishing to remove sharp edges and grinding to hold tight tolerances. Some manganese-zinc ferrites require a lapping operation on split-core mated surfaces in order to enhance electrical characteristics. Additionally, some parts will receive an insulation coating at this stage of either plastic or perylene, depending upon their application. We learned in previous slides that different ferrite blends can be processed to produce different electrical results. Now let's look at the specifics. Fair-Rite Products offers 10 different ferrite chemistries for EMI attenuation. The following are available in cable snap-it cores. FR75 is our low-frequency manganese-zinc suppression core designed to mitigate EMI from 100 kHz to 30 MHz. FR31 is another manganese-zinc suppression core and has the advantage of being very broad-banded, suppressing EMI in the range of 1 MHz to 300 MHz. FR43, 44, and 46 ferrite blends are nickel-zinc and attenuate EMI from 25 MHz to 300 MHz. FR43 and 44 are very similar, while FR46 is our lower-cost version, substituting magnesium zinc for manganese zinc. And finally, our FR61 is our high-frequency suppression material, suppressing EMI in the range of 200 MHz to 1 GHz. Another important parameter in choosing the right ferrite snap-it core is the diameter of the cable. The best performance will be attained when the core fits snugly on the cable. Round cable snap-it cores are available for cable diameters from 4.1 millimeters up to 33 millimeters. We can now express the EMI attenuation in graphical terms by normalizing the resistive impedance to 100% and plotting against frequency. As we saw on the last slide, our FR75 is effective at low frequencies. FR43, 44, and 46 are effective in the mid-frequency range. And FR61 is our high-frequency suppression material. Once we've determined which ferrite material will work best, the next step is to determine how much attenuation the core will give in the circuit. Knowing the impedance of the source and the load and consulting Fair-Rite's 17th edition catalog for the impedance contribution of the suppression core, we can calculate the attenuation. It is important to remember that the ferrite core's impedance is not a fixed number and varies greatly with frequency. Another factor affecting attenuation is the number of passes a signal-carrying cable makes through the core's aperture. Multiple wraps or passes greatly increases the impedance contribution of the core. Additionally, larger, longer ferrite cores will have more impedance and therefore better performance than smaller cores. Next, we will look at and calculate the expected attenuation of ferrite core 0475164181 and verify our calculations in the lab. We will test the formula by predicting the amount of attenuation snap-it core 0475164181 will give at 1.5 MHz with 3 passes through the aperture. The source and load impedance are 50 ohms, and after consulting Fair-Rite's 17th edition catalog, we find the impedance of our core at 1.5 MHz is 800 ohms. If we plug these values into our equation, we find the predicted attenuation is 19 decibels. The graph below shows the aforementioned effect of passing a signal-carrying conductor through the core multiple times. Passing it through 3 times through the ferrite core will give it approximately 9 times the impedance of a single pass. Many EMI problems cannot be solved with a single snap-it core, and if space and function allow, multiple passes might need to be considered.
Let's try to verify the calculation we made earlier by actually measuring what effect Fair-Rite has on a circuit. So let's review our setup. Here we have a current transformer. Here's our signal generator that will put out a 1.5 megahertz signal in the square wave form. We're terminating this with a 50 ohm load. Above it, we'll be measuring the output waveform on our spectrum analyzer. Here you'll see the fundamental frequency of 1.5 megahertz. You'll also see harmonics that extend out far into the megahertz range. Currently, without Fair-Rite, we're measuring the output at approximately 36 decibels. We know from our previous discussions, to attenuate a 1.5 megahertz signal, our FR75 material would work best. Here I've inserted a core with 3 passes through the aperture. Now let's take a look at the spectrum analyzer and see what effect it's had. We can see that the spikes are definitely reduced, and at 1.5 megahertz, the signal strength is now approximately 17 decibels, indicating that we've achieved approximately 18 dB difference by inserting the core in the circuit.
So we have learned that Fair-Rite can be thought of as a frequency-dependent resistor that absorbs EMI. It is manufactured by pressing certain metal oxides together and then fired in a kiln at high temperatures. Different Fair-Rite powder chemistries are utilized to mitigate different EMI frequencies. EMI attenuation can be calculated if the impedance of the load, the source, and the Fair-Rite is known.
Okay, we'll start our Q&A session. Audience, please continue to get those questions in. Our first question is, what causes the Fair-Rite to have high resistance at high frequency complex permeability?
Hi, this is Mike from Fair-Rite. So all Fair-Rite materials are going to exhibit an increasing impedance over frequency, and the different material grades are going to dictate what is high frequency by each material. But the complex permeability is what's going to dictate that overall impedance. So your impedance is going to be a vector of the reactive portion of the complex permeability along with the resistive portion. And as the frequency increases, that resistive portion is going to become more significant and eventually at a point dominant in contributing to that impedance of the Fair-Rite material. So it's from that resistive portion in the complex permeability that gives the Fair-Rite its resistive properties at high frequency.
Next we have, what do you do if the noise is too broadband?
So there's a couple options for mitigating broadband noise. One is going to be selecting a more broadband material. Certain materials are going to have a flatter resistive portion to their complex permeability, and that's going to allow them to give perhaps a lower overall peak impedance, but a larger impedance over a wider frequency range. There are a couple other options as well, though. Moving to a larger size core will have a similar effect. And another option, if the required impedance is very broadband, is to use multiple different core material cores in series with each other to give you a wider band of attenuation.
All right, thank you. Our next question. Are there common rules of thumb for estimating attenuation in circuits where source / load impedance are not well defined, e.g. push-pull digital drivers without specific output impedance? Or does one just have to use a network analyzer across the known load conditions?
Measuring, using a network analyzer across known load conditions is going to be the best method for trying to estimate that when you're uncertain about either source or load impedances. This is really, it does become a little bit of a guessing game when you don't have all those factors to enter in. And this is going to be characteristic of a lot of real world applications where you may not have necessarily a consistent load. So trying to characterize in as broad a range of conditions as possible is generally the best recommendation for doing that.
All right. Next, do you have any charts for quick guides to snap-on selections?
Well, for snap-on selections, actually, you want to handle this one, Bruce?
Yeah, basically our 17th edition website, a 17th edition catalog and our website gives quite a bit of information. You can find it at www.fair-rite.com. And you'll see frequency ranges along with the proper material selection for those particular applications.
All right, thank you. Moving back to ferrites, we have a question. Can ferrites be effective in reducing Ethernet conducted emissions?
Yes, in conducted emissions, yes. They're again, ferrites are available in snap-on form, and again, depending upon the frequency that you want to attenuate, ferrites are very effective from 150 kilohertz all the way up to a gigahertz and beyond.
And our next question, if the ferrite is not electrically insulated and is touching the enclosure of a product, will it make the result change?
That's going to be very dependent on what type of core material that we're looking at, and also what types of eddy currents are being conducted in it. So you have two main formulations of ferrite materials, and that's going to be nickel zinc ferrites, which are going to be generally higher operating frequencies, and manganese zinc ferrites. Now, nickel zinc ferrites have a very high bulk resistivity, so that is certainly of a lower concern with those types of cores, again, slightly dependent on the frequency. Now, manganese zinc ferrites, that can potentially be an issue if you're inducing large eddy currents within the core and the core is directly touching part of a metal enclosure.
Okay, next up we have, what about noise suppression above 1 gigahertz?
So noise suppression above 1 gigahertz, you're going to generally be wanting something like a nickel zinc ferrite. They do offer impedance for sure at frequencies greater than 1 gigahertz, and that kind of gets broken down into two categories also when you're talking about either shielding performance or if you're talking about conducted performance. In both cases, you generally are going to want something like a low permeability nickel zinc ferrite, like one of our 60 series, or in the case of a shielding application, our flexible ferrite lines do offer good shielding performance above that 1 gigahertz mark.
Next, we have a question. I have several snap-in ferrites that I use in the lab for testing. They're probably about 10 years old now. Does their performance degrade over time?
No, their performance won't. It's a crystalline material, and the crystal structure is locked. They will not degrade over time. They will be good for years to come.
We have a question. What about noise in lower frequencies, below or near 100 hertz?
Noise at those frequencies is really going to be, ferrites are not going to be very effective down at those very low frequencies. Down in that range, since the impedance offered by a ferrite is going to be a vector of the complex permeability in the resistive and reactive portions, at those very low frequencies, all the impedance, for the most part, is going to be reactive purely instead of resistive. And with the lower permeabilities of ferrite, relatively speaking, generally something like 20,000 or less, you're just not going to see a very large impedance value down at those low frequencies.
Okay, next, would you ever use two ferrite cores on a cable to target different frequencies?
Certainly, that is a very good and popular method for if you either have multiple harmonics that are substantial that you're trying to target, or if there is just a very broad band of noise that can't be covered by just one core material. That is a perfectly valid and very popular method of attenuating broadband noise.
Okay, we have a question here. Can we handle the issue of immunity testing using Ferrite?
You want to take this one, Bruce?
Yeah. We're going to take that question offline. We're going to do a little bit of research, and we will get back to you separately in an email. The question takes a little bit of research and probably a little bit of time to answer accurately.
Okay. Next, we have a question. Do you also offer nanocrystalline ferrite cores?
We do not. The process for nanocrystalline cores is very substantially different from the process of making the standard manganese zinc and nickel zinc soft ferrite cores that we produce.
All right. Next, what is the purpose of multiple turns using ferrites?
So multiple turns through a ferrite core are, in terms of a suppression sense, are going to exponentially increase the observed impedance of the core, or observed attenuation of the core. Now, there is going to be a trade-off, though, with multiple turns in that you will be losing some of the broadband characteristics of the core and also shifting that peak impedance frequency to a lower frequency with additional turns. But generally, the advantage is going to be a higher impedance and therefore more attenuation at a targeted frequency.
All right, we have a question here. What ferrites would be most effective for EFT issues?
We would like to take that one offline. That's going to be a little bit of a lengthy answer on that one.
Okay, our next question. I have several old ferrite snap-in cores with no numbers on them. How can I tell what core material they're made out of?
So pretty much the defining or main characteristic between the different core materials, that's going to be what we say is initial permeability, and that is the reactive portion of the complex permeability measured at 10 kilohertz at low flux density, and that low flux density is going to mean something less than 10 Gauss. So generally, the way you'd want to characterize that is going to be with an inductance measurement at or close to that 10 kilohertz frequency. Now, generally, they're going to be fairly flat between 1 and 100 kilohertz. So measuring inductance, and we have some formulas on our website for back calculating that inductance to a permeability number, and that will give you a reasonably accurate estimation of the core material that the ferrite core is made out of. And one other quicker, not as accurate way is to just simply probe the surface of the core material with a multimeter and just do a quick resistance check. If it's a very conductive material, that at least narrows it down to being a manganese zinc ferrite. If it's quite resistive, then that will give you an indication that you're looking at a nickel zinc ferrite.
Okay, next we have, in general, assuming there is a price delta between materials, which materials are the most cost effective and which ones will cost the customer more to use in their applications?
In general, bigger ferrites will cost more money. They'll also tend to be more effective at attenuating EMI. I'd like to remind everybody it is snap-ons are kind of a last effort in combating conducted emissions. It's always easier to take care of it at the board level with surface mount components and through-hole components. And those components tend to be in the penny range. Snap-ons are in the dollar range, several dollars. So as a last effort, we also offer our 46 material, which is a lower cost version of the nickel zinc and manganese zinc. In general, like I said, it's always better to take care of it at the board level and lastly at the snap-on level.
Okay, we have a question. For noise between 100 megahertz and 500 megahertz, does it matter which order the cores are stacked on the power line?
No, if we're using multiple, I guess just to clarify, if we're using multiple different material cores in series along the power line, it really shouldn't make a difference the order which the cores are stacked on the power line. The only maybe caveat to that could make a difference is if you're using the cores in more of a shielding sense, and that's going to be a little bit difficult to estimate depending on what signals are hitting where along the power line. But in general, no, it shouldn't make a difference.
Okay, well, I think we're running close to our time here. So thanks again to Bruce and Michael from Fair-Rite Products for the demonstration. If we weren't able to get to your question live today, don't worry. All of the questions submitted will be posted on our website along with answers. Watch out for an email from us within the next 24 hours. We'll be sending you a link to the on-demand version of this presentation. Once again, I'm Jennifer Arroyo with Interference Technology. Thanks for joining us today.
Thank you.